So we know that data values can be stored in specific RAM locations. So we've done this directly before using constants. So for example, the following code stores the number 99 in RAM location 3. So the first thing to do is set the A register to the value 99 using the @99 syntax. And we can copy that value into the D register as a kind of temporary buffer. So here D will be equal to 99. Then we set the A register to be equal to 3 using the syntax, and then M equals D will then copy the contents of D, so the value 99, into RAM 3. So we've done that before using constants, but we'll see there's another way to refer to memory locations, and that's by using symbols. So in the hack assembler programs, there's 3 different types of symbols you'll come across. There's some predefined symbols, there's label symbols, and then there's variable symbols. So the predefined symbols, they come as part of this platform, and they're made up of some virtual registers. So actually RAM addresses 0 to 15, we can refer to them using the symbols R0 up to R15. So that's 16 registers in total, so R0, R1, R2, R3 up to R15. Now even though these registers are just kind of actually RAM addresses, it mimics the architecture of typical processors that have these small number of registers actually inside of the CPU. So these ones are not actually inside the CPU, they're inside the RAM, but it just mimics what you do see with a normal processor. Then there's various predefined pointers, so SP, LCL, ARG, this and that. They're predefined, and they refer to addresses 0 to 4. So you can actually, so 0, so we know R0 to R4, for example, there would be 0 to 4, and then these also refer to 0 to 4. So these can be used together. So R0 is the same as SP, for example. They both refer to 0. So these, we don't actually need these in this part of the course. These are used in a different part of the course, looking at the virtual machine. And then there's also some predefined symbols for the I/O pointers. So these 2 input-output devices that make up the computer. We've got the screen and the keyboard. So the screen, that refers to this memory location, and the keyboard refers to this memory location. So these are just the base addresses of the I/O memory maps. So this is a kind of example architecture of a computer. So we'll see. So this is normal. This is representing the CPU. So normally we do have these registers actually inside of the CPU. So some register bank. So this, so in this example, there's 8 registers inside the CPU. So R0 to R7. So in this kind of hack assembler, there's actually the first 7 slots in. If we assume this memory is a RAM memory, the first 7 slots are referred to as R0 up to R7. So this just mimics what you do see in a normal CPU. There's also label symbols. So on top of the predefined symbols, we've got label symbols. Now these are what are defined by you as a programmer. So these are user defined, and they label the destination of jump commands. So we use this kind of bracket syntax. So inside the bracket you've got the name of the symbol, and that refers to the instruction memory location which holds the next command to be executed. And if we want to jump, we jump to the specific instruction in memory, and this label will be used to refer to that instruction. So basically it's a value that's going to be loaded into the program counter, and these labels can only be defined once in the code. These label a specific place in your code. So you can only define it once. Then we've also got variable symbols. Again, these are user defined, so you use these when you're writing your program. So we've got any symbol. So I'll just call it XXX here. So any symbol that's not a predefined symbol and it's not a label, it's treated as a variable. So the symbol is automatically assigned a RAM address starting at 16. So we know R0 to R15, they kind of represent the first 16 slots in memory, 0 to 15. So the first time that you use a variable, so in this example, suppose we use a variable symbol called sum, so we're at sum. That's not a predefined symbol, and it's not, assuming it's not been a label either. At sum will refer to address 16 in RAM, and then again we have another label, so at total. So this next variable when this stored in 17 and so on, because that's all variables are in software. A variable is just the name of a memory location rather than actually specifying the memory location. It's obviously very easy. If you're only dealing with a few memory locations, you know, you can maybe start remembering the actual addresses. But as soon as you start writing any kind of complex software, you have lots of different. You're going to be storing lots of different data. It'd be impossible to track the exact memory location of each bit of data, so then we can just use a variable to represent that. So the variable is just a name for a specific area in memory where the data is stored. So there's various conventions and syntax that you should stick with. So constants must be non-negative and written in decimal. Symbol names can be any sequence of letters, so we can use upper or lowercase letters, numbers, underscore, dot, dollar, and colon. So symbol names cannot begin with a digit, so you can't call symbols cannot begin with a digit. So the various conventions you try and stick to. So variables we keep as lowercase. So it's at sum, for example. Labels are uppercase, so we might want to have a label to represent a loop, for example, so we use uppercase. And then the commands, so the various computations we're doing, mnemonics are also uppercase. So this is might want to do M equals D or something like this. So white space is ignored. So when you're writing your assembly code in the text editor, white space is ignored, so you can use that to kind of split into nice chunks and make it a bit easier to read. And then also we can, just like in C, we can use 2//, and this denotes a comment that gets ignored.